ஷேர் பண்ணிட்டீங்களா?
இல்ல வேண்டாம்.
ஷேர்.
ஓகே ஓகே.
எழுதுறாரு. Rule. Where is the rule one, sir? This one, right, sir?
No, this is okay.
It is okay, sir. ஷேர்ல இருக்கா?
ஆமா.
ஷேர்ல கன்ஃபார்ம் இருக்கா?
Share.
Don't close it. Otherwise it will be hard for me to. Yeah.
Leave it like that.
So if you want video means just click this one. Yeah. All these also on. Audio is already on. Yeah. Yes. Good evening all. I hope I am audible. Can one of you confirm?
Yes, sir, it's audible, sir.
So today I will just review quickly about that this week's lecture content which you have already gone through. Primarily we are looking at drag. It may be a good time for you to revise also the concepts of lift and drag which you might have learned in your earlier weeks, like 1 or 2 starting weeks. The context in which the drag was told to you was from 1 second please. And annotation only for this. Others this is
The only part.
okay. Nobody else can write.
Yes.
Okay. And then when it's fully, then it's hard for me to come back, get it back. And that's okay. Yeah, thank you. So we were talking about drag being used for some from advantages for some advantage, especially from the from reducing the speed. Just like in the case of road transport, we will talk about friction. Here we have drag, but you should understand that drag and lift are just some two ways to look the overall aerodynamic forces. And what I mean is, if you have an object, let's say a flat plate, and if it is kept at an angle of attack, by now I believe you know what is an angle of attack. This is the flat plate, and the flow is at some angle to it, or other way. This is the way the flow is. The plate is kept at an angle here, and this is what is called as angle of attack. Now we know that there is some resultant aerodynamic force. That is, there is some aerodynamic force acting on the object. It may be in some direction, and we prefer to call that direction to be consisting of two different components. So we call one as lift and one as drag. And lift happens to be perpendicular to the free stream. Free stream, I mean the velocity which the wind is hitting the object. You should not think that this is the velocity, whatever velocity we talk about, it's a velocity near to this. What we say v when you talk about lift is half rho v square SCL. This was taught to you in your earlier lectures, if I'm not wrong, by Professor Bharat. Can someone confirm? No? Or maybe in the context of airfoils as half rho v square c CL is lift per unit length. Was this taught to you?
I don't think so.
No. Okay. So when you have an plate, for example, or any aerodynamic object for that matter, typically what is seen is, this is called the dynamic pressure, half rho v square. Rho is the density, v is the velocity. So v is the velocity not close to this the plate, but far down. So if you can think like this, if an airplane is moving, so this is an airplane, this is moving at some velocity v, and if I want to equivalently see the same airplane aerodynamics, I can fix the aircraft at zero velocity and then have a free full, let's say you're thinking putting it in the wind tunnel, you may keep this airplane model inside the wind tunnel, and there will be flow through the wind tunnel. I presume that you know what is a wind tunnel. Wind tunnels are just like you have some big chamber or a pipes kind of thing, and there is a flow pumped through it at some constant velocity. It usually is in a very controlled manner, reducing the disturbances, etc. The idea is whatever aerodynamics you may see from the airplane moving at some velocity can be simulated, or same environment can be produced by keeping the airplane fixed and having a velocity through the wind tunnel at the same velocity like v, or velocity or speed. In this context, it doesn't really matter because it's only in one direction which you're looking at. In any way, the idea is when you talk about lift and drag, they're just the forces we are looking in two different directions. The combination of this is what the actual aircraft or the uh, airfoil or plate, whatever aerodynamic object it sees. So if you have a spherical ball, for example, whose projection is what I'm sketching here, let's say you are dropping it from a large height or maybe a big mountain. You're just dropping it. So it will fall down and its velocity is going to be different from what it would have been if there is no atmosphere. So the classical way you learn in your in a physics class in a school is when you look at the velocity as u plus gt or ut plus half gt square and so on. All this is assuming that there is no other force exerted on the body, exerting on the body apart from the gravitational force, and that too constant gravitational force. So this is the approximation we're making. Now, when you're dropping an object in presence of atmosphere, that is, say you're in the mountain on Earth, which means there is significant amount of air here, there will be drag or some atmospheric force that will, or some force is exerted by the atmosphere on the object that will change how the body will move. So this is a very simple scenario because there is only, it's a spherical object, so it wouldn't matter. There is nothing like an angle of attack that is now of importance because it's symmetrical. However, where you keep it, it doesn't make any difference. So it will be symmetrical. There is nothing to talk about an angle of attack or anything. So you have an spherical, think of a ball, you are just dropping a ball. So there will be some drag force exerted on the object in the opposite direction. Typically, that is given as half rho v square. Rho is the density of air, v is the speed at which it is moving. Uh, S is the project. So in case of spherical ball, it will be instead of the 4 pi r square as a surface area, we look at the projected area. Actually, it's a convention rather than saying that that is only a way to. We could have well done with 4 pi r square, but only thing is the difference is the CD, the coefficient of drag which you talk about will be now different. So this is the overall drag force. What I mean by S to pi r square is just think that you are measuring. You can think of this way. Suppose there is this ball and you have kept it in a wind tunnel. Okay, this is the ball now, is a wind tunnel. Now you are measuring the drag force that is experiencing. So you can think that there is some device that is kept here. You can even think that there is a spring attached to it here back. So how much ever it is compressed backward, that will tell you how much it was. Just like the way you have a weighing balance. So think that such a simple device is there, and you are able to measure the force exerted on the ball. Now there is a flow, so there will be some drag. So there will be some force that is being measured. Now imagine that the density is now constant here. The flow you're doing it is the same ball which is kept. At different velocities, you may start measuring the forces. You will see that the force that you measure with respect to velocity will go as v square. That is, it will be some proportional to v square kind of graph. That is what you'll observe. And if you divide that half rho v square and s being as pi r square, you call it as coefficient of drag. You could have well done with 4 pi r square, in which case the CD or the coefficient drag which you get will be having a factor of 4 in the denominator. That's not very important. It's just a convention. So you take it as pi r square as the area. So core idea is the drag force that the object experiences is proportional to half rho v square. Okay, this is true for lift as well as for drag. Now, the crucial point here is that the lift and drag is just two components, or is just one resultant, or the total aerodynamic force we are dividing into two different components. One is in the vertical direction, one is in the horizontal direction. Or more correctly speaking, one lift is in the direction perpendicular to the velocity, and drag is along the direction of velocity. If you are not familiar with vectors, especially 10th standard students, you may find it little odd here. But you just think that these are just forces acting on the object. Just think that way. Lift is one force, drag is another force. Although they both are components of one same force that is exerted, total aerodynamic force that is exerted on the object. In the case of the spherical ball, it is only the drag that you see because there is nothing like lift because it's symmetrical. So idea is there is some drag force that exists. There are different reasons why drag can exist. Uh, there are different names also you may hear: profile drag, parasitic drag. Keep all those things aside. You can just think that now there is some force that gets exerted on the object in this direction of opposite to the direction of its motion. So if you drop a ball, you will see that half rho v square s into CD will be acting on the object, which would also mean that the new page. Okay. So if you think there is an object and it is falling down, if it is falling down at a constant velocity, that would mean the drag it experiences will be equal to its weight. Half rho v square s into CD will be equal to its weight. So if it is moving at constant velocity, which means there is no acceleration, and by Newton's law, you know that if there is no acceleration, the velocity is constant. That means there is no net force acting on the object. In this case, there are only two forces that are acting. One is the gravitational force, one is the atmospheric drag force. If both are equal, that means object will be at constant speed. It will descend at a constant speed. This is more or less how parachutes work. I'm not saying that all parachutes work only because of drag. Some are designed to use lift also, like parafoil. They use lift also. There are reasons why you want to design it that way. But nevertheless, let's look at only the drag for now. You have atmospheric drag that slows down the object, and at some point it will be equal to this weight, and it will be moving after constant velocity. So you can think of this: if the ball starts dropping, initially the velocity is zero, it will gain speed at some point. So when it increases the speed, remember that the drag force also will increase. So you can think of this way: when its speed is increasing, the drag force will be increasing. Okay, and at some point the drag force will be equal to, so this will mean the velocity will not so if it was constant velocity, so you should think that let me put it in a slightly different way. We know that the velocity increases, the drag increases, but you should also understand that with respect to time, it will slow down because the rate at which the velocity will increase will be lesser. So for example, the g, or the gravity with which it was earlier accelerating, or the body was coming down, will be different now. It will not be g, because there is another force which is the drag force that is acting on the object, and the drag force will keep on increasing with velocity, and at some point that velocity will be equal to the drag force will be equal to the weight, and the object's velocity will be constant. So with respect to time, if you plot, you may have the velocity going up and it will come to a constant value later. And this will be the steady speed at which it will descend. Okay, I'll pause here. If you have any questions on this, I'll be happy to answer now. It's a very fundamental concept, and I presume most of you should be able to understand it, so that it will give you an idea of, I mean, it's not only about the drag, this is more or less how the different objects move in flight, just that you have more parameters coming in, lift coming in, and so on. Any questions? Are you all understanding what I'm talking about? Can at least somebody confirm if you have understood?
Yes, sir.
Okay, good. These
Yes,
things are
sir.
taught to you in your earlier lectures? No. Okay. Any questions on this?
No, sir.
Okay. So there is one more thing I would like to add. You should understand that the velocity which you're talking about here refers to the relative velocity of the object with respect to the wind. This is also important because let's imagine for now you are okay. Think of it a long tunnel. Instead of having the gravity here, let's remove the gravity. You have a long tunnel, okay? It's a wind tunnel. And for some mechanism, you had put a ball here. Maybe you can think of a small ball, and there is a small line along which it is attached. So it can just skid through this, or it can just go along that line. You can think of a small rope or a thin rope on which it is centered. The ball is centered and it's moving along the rope. That is, you are just given the initial velocity, it starts moving to the front. Imagine at the other end there is a wind tunnel and it is blowing air from the other side. What will happen? Just like the scenario which we just explained here, the velocity will start dropping, and at some point it will come to a standstill, and then it will start going back in the opposite direction. Now, thing you should understand is the velocity with which it is moving with respect to u, which is or the wind tunnel which is fixed, is not what you should use here for the drag force. So I'll put here, for example, I'll put a small subscript g, ground speed, which is with respect to the ground. Now the speed at which, or the relative speed, in the sense that if suppose it's just like the way you are running into a wind, you will experience more drag than when you are running when there is no wind. For example, if you are playing cricket and if you're bowling, you're trying to bowl against the wind, you'll definitely feel more resistance. You'll be finding harder to bowl. So that is why in cricket, you sometimes you feel there is an advantage when the bowlers are bowling with the wind and opposite of the wind. So you have a scenario where the relative wind, which is to be considered. So here they are opposite. So which means the effective speed which the ball sees from the air would be Vg plus, if this was Vw, Vw. This is the total. So your drag force will come out something like this. Okay, that is why when there is a wind, there should be more drag force because effective or resultant velocity which is coming into play. So the relative velocity means with respect to an object. So if the relative to air, what is the velocity? So if the air is moving, which is the wind, the relative velocity will be different. If when it starts moving in the opposite direction, your relative velocity will be minus, because with respect to the wind, you are having a different speed. Okay. Now this gives an overall idea what is v, which is the relative velocity. You can have drag. Similarly, you can have lift also. You should not think, as I said, lift is always vertical, because in this case, when the object was dropping, really coming down, it's the drag force only that was operating. The similar things act when same thing is applicable when you're talking about an aircraft or any other aerodynamic object. There is a lift and the drag force, and you write the equation summation. For example, here it would be mass into acceleration, with acceleration being defined positive downward, mg minus half rho v square is v. You cannot solve this very easily because this acceleration is the rate at which the velocity is changing. If you are familiar with calculus, which you may be doing in 11th or 12th, you will see acceleration to be written in dv by dt form, and it will be a differential equation which you have to solve. For school students, in 10th and below, you can just ignore this. Whoever has probably seen this calculus, you will appreciate this better. But it's not essential for what we are talking about next. So it will be a differential equation rather than algebraic equation which you need to solve to find how the velocity will evolve in with respect to time. That's why I said it cannot be simple equation like what you would have got when you solved for like u equal to v equal to u plus gt in the form where g was constant or acceleration was constant. Any questions?
Sir, I have a question. Within this equation, can you please explain what is SCD doing there? I don't know the meaning of it.
This is what we explained in the previous first page, where when you measure the force, okay, you can think of this. You have an object, okay, let's say sphere, okay, and now there's the same flow here. I measured the drag force that is exerted on the object. Now, logically, if you had to use a bigger ball and at the same speed of it is thrown, you should expect more drag force, no? Because there is more air that is getting in contact with the object, correct?
Yes, sir.
So in that sense, you understand that there is somewhere the area is going to affect the amount of aerodynamic force or the drag force that is being experienced. Who is writing there? Please stop. Yeah. So the drag force that is being experienced with the object will be proportional to area. So that is how S has come. CD is just a convenient way for us to represent this fact. For example, if you are talking about spherical balls, now if you want to measure the force, what a naive way would be? Okay, you take every time you build a spherical ball and you are doing the aerodynamics, put it in a wind tunnel or do an experiment to measure the drag that is being coming here and so on with each velocity. But that is too much of a work. Everybody cannot do it all the time. So what do? we understand that we measure the force, that is the drag force that is being experienced by the object. We understood that it is also somehow connected to half rho v square. We also understand it is somehow connected to s. Now suppose that you divide d by half rho v square s, and if you see that it is constant, sometimes it may not be constant because it may be a function of v, but for our first approximation, this comes out to be constant. Suppose you use different balls, different dimensions of the ball, and then measure the force and at different velocities, but every time you find this quantity, that is d by half rho v square into s, you will see that it will be a constant. So now it is an easy way for us. We just have to take one ball, you put it in a wind tunnel, do the experiment for one velocity, measure the force, divide by this force by half rho v square s, whatever you get, we call it as CD. Now at any other speed you want, let's say it's half rho v2 square, that is some other velocity v2, what will be the force? Or maybe a bigger ball, let's say area is s2. You just have to measure half rho v2 square s2 into CD, because we know the force by that half rho v square is a constant. So this idea of representing non-dimensional numbers, I mean using non-dimensional numbers, is quite very handy, because you don't have to do many experiments. You can do with respect to, in this case, only one parameter, only velocity, and that alone, if you do, you can find out what will be the drag force for any other velocity or surface area. Did I explain what you had doubt?
Yes, sir. Thank you, sir.
Okay. Anybody else?
Sir, I
Uh,
have a doubt, sir.
Yes.
Chandrasekhar. Sir, I ask in general, sir, why we instead of using the old parachute like in round shape, instead of that we using a dome shape, sir. Nowadays,
I didn't get your question. Is it
the
sonic?
shape difference, sir.
Sonic
Shape.
So there are different there are parafoils which are much more like thinner way, and there are like this which is primarily based on only drag. So both ways are acting. Both. I don't know which one we are talking about. Is it this one you're talking about, which is little more flatter, like a more like a small bow? They
Yes, sir.
they operate with lift and drag. Lift will help to travel longer distances, especially. So it makes sense. It is like more like a gliding, where aircraft gliding, and
Oh,
this will be much more similar. This kind of structure, where spherical, which you're talking about, will be more based on drag. Usually that's how it is. And there are also differences
okay,
when
sir.
very high speed parachutes, like when you're talking about supersonic drag and all, which experience. So there are different designs that are required. Maybe different stages also will be there. Okay.
Okay, sir.
Any other questions? Any other questions on the lecture content we had? I also mentioned about glide. I don't know, did I talk about glide in the presentation? Glide and what do you mean by soaring? Can somebody confirm? You all know what is soaring? You see the birds going around in circles without losing altitude nor flapping. Ever wondered why it happens?
So it's because of a vortex, right?
No, not necessarily. I mean, there are ways you may model it, but that's not how why it is. It is so. Why how birds? I mean, I'm not talking about all scenarios, but most scenarios they don't do it at all places. Some places they lose height, but there are occasions you will see birds not losing any height, but they'll be going around in circles. The same thing is quite often exploited by gliders also.
Sir, is it due to the warm air?
Yeah, it's some sense correct. Warm air means there is something called the updraft. That is, it moves up. So there will be regions on Earth's surface, close to the Earth's surface, where you will see there is warmer. So there is, as you said, the temperature difference will make sure there is some air that is going up in one region and it will come down at some other region. Okay, so let's ignore this part. There is some region where the air is going upward. And gliders or birds, when they are there in this this region, they can utilize this and fly even without any power. And how does it happen? The same concept we just talked about, the relative speed. So if you have an aircraft that is moving at a velocity v, let's say, okay, and there is a flow that is coming from the downward direction. It may not be obvious to you if you are not familiar with vectors, but it would mean that the related to this air or this aircraft, if you think that this aircraft is still, so as I said earlier, if there is an aircraft is moving at a velocity v, it is equivalent to a scenario where aircraft is at speed 0 and there is a flow in the opposite direction, which is v. Now, if you have an aircraft is moving at a velocity v, and which equivalently mean the aircraft is still, there is a flow in the opposite direction, which is v, and there is a velocity that is from the wind coming in the upward downward direction. There effectively the combination of these two will be at some angle in this direction. Okay, I don't know without vectors how do you see it, but just for now take it for granted that when you have these two components, the resultant or the effective velocity which the aircraft will see will be in this direction. You can think of this with the classical example given is about when you are cycling and you have rain coming at you, you would see the rain to be at some angle. So it is just this is a crude example to tell you that okay, this is related to you how things change. So that is what the relative velocities, and in this particular case, it will be at an angle with respect to the aircraft motion. The idea is now this is the aircraft motion. Effectively, this is the way the wind is blowing to the aircraft. Equivalently, now you can also think that it is the same scenario when the aircraft is moving downward in a particular velocity. So if this is the total velocity, let's call it as A, at which it is seeing the aircraft is seeing, it is equivalent to the aircraft moving at that A velocity at an angle. So the same scenario, as I said, these two are equivalent. So idea is an aircraft which is being in updraft where the air is flowing from bottom to top is very similar to the scenario where aircraft is gliding. And you know that when aircraft is gliding, intuitively you can see that when an aircraft is gliding, it doesn't require power because the gravity is going to compensate for the drag. I am not sure how many of you will be able to appreciate this, but see if you can understand the principle. So this is how actually the birds are able to utilize updrafts. They are typically called as updraft. Or there is an upward flow velocity in a region. So there is air flowing from bottom to top. So this updraft will give a provision for the birds to effectively fly as in glide. So they don't really lose altitude. They just able to sustain the flight without using any propulsive mechanism. That is, they don't have to flap wings. Yeah, you can go ahead with your question.
Sir, this is like dynamic soaring.
That-
Isn't there also a thermal
Dynamic soaring is
component to it?
No, dynamic soaring is different. If you want, I can explain that after this. Dynamic soaring is slightly
So
different.
that uses wind shear, right?
It uses wind
So,
shear, not this updraft. It's actually the principle is very different.
all right, sir, if you could explain that, that would be wonderful.
I'll explain that. Any questions on this soaring? So this is called soaring. Sorry. This is called soaring, or sometimes just to be more clear, you can call it as thermal soaring. Okay. Now let me explain since you asked about dynamic soaring. So this is quite interesting. Why? Because you won't understand at first glance when something of this is seen why it happens. So its observation came from long time back. So in 1860s or something like that, or 1818s, there was one person called Peel, I guess his name was. He was in Assam, our state, and he observed that there were birds. There is a mountain range, and there were birds that were flying without flapping wings in a particular form. Now, it was not obvious, he did not know why it happens, etc. But he reported that in one of the journals, I think Nature only, at that time. It's a long time back. Then there were Lord Rayleigh was there. He proposed some explanation also why this could happen. Now, after that, there were many observations, but it was not in land, but more in oceans, like albatross. The birds like albatross. Many people used to see that when they go in ships. What happens is the birds will fly in a particular fashion. They'll go up and down. So let me show it in a different way. So this is a water surface, and the birds will come down, then climb up, down, climb up, and so on. So they will fly in a particular fashion. But throughout, the most interesting part is they won't flap. They won't flap the wings at all. Nothing. And they're able to travel long distances without any flapping. But what differentiates this from a normal scenario is there'll be wind. There can be wind in different directions, but usually in the cross direction. That is, the wind may be in this direction. That is, you should see from the 3D perspective that okay, you can think like this. The bird is flying from south to north. So this may be south and this is north, and the wind is from west to east. So it will fly in a particular fashion that says it is able to fly in from south to north. There are different ways it can do. I mean, it can be along the wind, same direction also it can fly, opposite also. All things are possible, but the maneuvers is slightly different. The idea is there is something called the wind shear, and wind shear is that when you are very close to the surface, actually, if you're on the surface, you should experience zero wind speed. You can't, this is in fluid mechanics, you may call this no slip condition, but forget about the technicalities. At the surface, you will see zero wind speed. As you start increasing the height, the wind speed will start increasing, but the rate at which increase will be reduced. The idea is that there is a grade, not the grade of something called mathematically we call it a gradient. There is a difference in the wind speeds as you go up in the altitude. Now, this difference is what it actually utilizes. It may be difficult for me to explain the whole principle or the logic behind it, but I will tell you what happens. Other things, the technical time I have to get into some maths and some other concepts which you may not be aware, but I'll tell you the basic principle. There is a wind velocity here, which is very low in magnitude, because as you said, as we said, the close to the ground, it is low velocity. As you increase height, it will be higher velocity. So very close to the ground, it is very low velocity, and as it increases, the velocity will be higher. Now, what albatross does is it will make one turn very close to the ground or water surface. Actually, you can see its wings will be almost touching the water surface or the waves, and then it will climb up. Then it will make another turn at a higher altitude, maybe 20, 15 meters or 10, 15 meters, 20 meters at the max. Then come down. But when it makes another turn here, it sees a higher wind speed. Then it comes down, then goes up, and so on. Same thing it repeats. Now, there are two different ways you can see this thing. One, from the context of a pseudo force, which I don't want to get into, because there is an accelerate. You can think that accelerations are different, or the wind field here, since the gradient, there is a difference in the wind speed. There is something called the pseudo force that may come in. Let's leave that. Other way to see that would be you can think of it very simply. The energy from the wind is extracted at the higher turn, and energy is rejected back to the field or the wind field from the lower turn. But since this happens at a higher speed and this happens at lower speed, there is a net energy gained by the bird, and it is able to fly continuously without flapping its wings. As I said, it may be a bit hard for me to explain without going to the math or the theoretical part in detail. And with the current background you may have, it may be difficult. But at least this you can understand that this wind shear, or the difference in the wind speed at different layers, is what enables the albatross to fly long distances. This is very much different from what you are seeing from thermal soaring, or when you might see eagles flying at constant altitude without flapping the wings. They could fly. I mean, you can also see birds flying in a helical path and coming down. That is also fine. Even though there is no updraft, they can do it without flapping, which is something like a turn and a dive, or the glide, which we just talked about. But it could be, if there is an updraft, then this sink doesn't happen. It doesn't have to lose altitude. It can sustain at the same altitude. So in both scenarios, what you can actually see is the birds are able to exploit whatever is available in nature to the fullest advantage. And this also is something which we use with the gliders. Yes, we use thermal adapter, but this is dynamic soaring implementation much more harder, because you have to fly very close to the ground. The maneuvers are a little more harder, but the concept is still promising for us to use. I hope I explained. Who was asking? Shrey was asking this?
Yes, sir.
Did I explain at least to some extent?
Yes, sir.
Yeah. Anything else?
No, sir.
Okay. Anybody else? Any questions on the content which we had for this week?
No, sir. Completely understand, sir.
Okay, good. So if no more questions, then shall I wind up? Okay, then I hope there is nothing more to discuss this week. So one last time I'll ask, anybody else, any other questions? If not, I will end the meeting. Okay, thank you. I'll see you next week. Bye.
Thank you, sir.
So.